So for the rest of this set of notes, we're basically just applying the rules that we talked about in the last video. The idea is just that we want to do as many examples as possible to try getting comfortable with the selection of U and the U substitution process in general. So I just want to run through as many examples as we can to hopefully get you a little more comfortable with deciding what U should be and then integrating whenever you get rid of X. So let's look at example B here. Remember that what we're trying to do is undo the chain rule. So we're looking for the inside function here, and we also want its derivative to appear somewhere on the outside. So maybe I'll scroll up for a second. Notice that in the chain rule, over here, we have an inside function, which is g of x, and we also have the derivative of that sitting around somewhere on the outside. So if we're trying to undo the chain rule, that's what we're looking for. We want an inside function somewhere with its derivative sitting around on the outside. And that gives you a good hint as to what U should be. So if we look at this example, I want an inside function whose derivative is sitting around somewhere on the outside. So that looks to me like it should be 5x. So let's try that one. And by the way, it's okay to just try a U substitution and see if it works out. If it doesn't, then maybe rethink what your U is. So here, I'll let U equal 5x. That looks like my inside function. And then I'll take the differential on both sides. So I'll get that du is equal to the derivative of the right side, which would be 5, times a dx. So if you continue writing things in this notation rather than the fraction notation, then you'll always end up with a du on the left side and a dx as the last factor on the right side, if that helps. But it would also be okay to write this in terms of the derivative notation that we've been using so far in this class. You would get the equivalent equation, du dx equals 5. And then if you really wanted to, you could rearrange this to get du is equal to 5 dx. So either of these would be fine. But now let's use these to try rewriting this integral in terms of just u. So we have e to the 5x times 5 dx. Now the 5x is just u. So anywhere I see a 5x, I should replace that with u because I'm trying to rewrite this integral all in terms of u. And then secondly, I have a 5 dx here. But notice that 5 dx can be replaced with a du. So this outside would just become a du. And now we've successfully replaced all of the x terms with u's. So now we're integrating a function of u with respect to u. So now we can just compute this integral like we normally would. The integral of e to the u with respect to u would just be e to the u. So notice that it doesn't matter what this variable is. So calling it u or calling it t would also be fine. So we could also rewrite this in terms of a variable t. If I didn't want to call this function u, I could call it t, and this would still work out to be exactly the same. So the name of the variable doesn't really matter. What matters is that we're integrating a function of u with respect to u. And there's no reference to x here. So this will just be the ordinary integral of e to the u, and then plus c. And then as our final answer, remember that we want to take any u's that appear in this answer and replace them with the expression in terms of x, because ultimately we were looking for the antiderivative with respect to x here. So I want to take this e to the u and rewrite it as e to the 5x plus c, and that would be our final answer. So that's what we want in that first one. And remember, I think the main point here is that we're looking for an inside function somewhere whose derivative or something like its derivative is sitting around as a factor on the outside. So let's try to do something similar here in problem C. So in C, I'm looking for an inside function whose derivative appears somewhere. So what I notice is that in the denominator, I have a 4 plus x squared, and the derivative of that is sitting around up here. It's a 2x. So if I see something and its derivative sitting around, then it's a good idea to maybe let u equal that something. So I'm going to try letting u equal 4 plus x squared, because that would simplify the denominator a lot. Instead of a complicated denominator, the denominator would now just become u. So that would be nice. And if I take the differential on both sides, I would get that du is equal to the derivative on the right side times a dx. So that would be a 2x dx. And this is the u substitution that I'm going to try. So with this u substitution, I would get that the integral that we started with, which is the integral of 2x dx divided by 4 plus x squared. Now, the denominator I know I can replace with a u. And in the numerator, I have a 2x dx, but I know that that 2x dx can be replaced with a du, just from the differential equation that we have over here. So this would become a du over u. If you'd like, so you can treat du as sort of a multiplicative factor. You can never take it out of the integral. It's part of the integral, but you can rewrite this as a 1 over u du if you want to write it that way. These are equivalent. But now we've successfully gotten rid of all of the x's, so I'm just trying to integrate 1 over u du. And we know from our rules last week that when you integrate 1 over x dx, you would get ln of x. So that means when you integrate 1 over u with respect to u, that should be ln of u. So, and technically you should have absolute values here. So this would be ln of the absolute value of u plus c. That's the value of your antiderivative. And then as your last step, after you've done this integral, you just want to replace u with its value in terms of x. So this would be ln times the absolute value of x squared plus 4, or 4 plus x squared, if you want to write it in the other way, plus c. So I just replace u with its value in terms of x, which was this. And it doesn't matter which order you write the terms in. You could leave it as a 4 plus x squared. I just normally like to write the highest power of x over here to the left. So that's what we get as our antiderivative. And by the way, if you aren't really sure whether you're computing these correctly, you can always just try taking the derivative. Sorry about that. You can always just try taking the derivative of the expression that you get at the end. So maybe, for example, up here, up here, if you take the derivative of e to the 5x, then that would be e to the 5x times 5 by the chain rule. And then you can check that that actually is the integrand that you started with. So e to the 5x times 5. When we integrated that, we got its antiderivative was e to the 5x. Therefore, the derivative of that should get us back to the integrand, which is e to the 5x times 5. So this confirms that we did get the right integral. So you can always check your answers in these by just computing the derivative of whatever you get for the antiderivative. So that gives you a nice way of checking your answers.